Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. You are invited to join us for the very first TWIMLcon conference, which will focus on the tools, technologies, and practices necessary to scale the delivery of machine learning and AI in the enterprise. The event will be held October 1st and 2nd in San Francisco, and early bird registration is open today at TWIMLcon.com. Again, that's TWIMLcon.com. I can't wait to see you there. All right, everyone. I am on the line with Gerry Zhang. Yunfan is a PhD student in the Department of Astrophysics at the University of California at Berkeley, and is also affiliated with the SETI Research Center at Berkeley. Gerry, welcome to This Week in Machine Learning and AI.
Thanks, Sam. Thanks for having me.
You spend your days searching for extraterrestrial intelligence. Let's just start right there. Tell us about that effort at Berkeley and how you got involved in applying machine learning to that search.
Right, absolutely. So SETI, which is short for the Search for Extraterrestrial Intelligence, is about the question, are we alone in the universe? So the search for extraterrestrial life comes in many different forms. Many searches involve searching for simpler life by looking at the biosignatures, or by going inside of our solar system, doing in situ sampling in the soils on Mars, for example. SETI takes a slightly different approach. So SETI is the main idea behind SETI is that a lot of technological signature or radio emissions, whether intentional or non-intentional, could potentially be detected from very, very far away. Therefore, if there are advanced civilizations within our galaxy, we could hope to detect their techno signatures with our existing telescopes. So these ideas have been proposed since the 1950s, and since then we have greatly increased the computational as well as the analog capabilities. And in 2015, the Breakthrough Initiatives was funded by Yuri Milner. The Breakthrough Listen project in particular is a $100 million project to conduct the most comprehensive SETI to date. And the main headquarters is here in Berkeley at the Breakthrough SETI Research Center, where we analyze the data that we collected from currently two main telescopes, the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, and most recently announced the Meerkat Telescope Array in South Africa, which is a precursor to the Square Kilometer Array.
Oh, interesting. Now, I remember back in the early 2000s, I guess, there was a SETI at Home project, which basically kind of distributed, there was this client you can download, and the SETI at Home project would kind of parcel out these mathematical equations, basically analysis of some set of these, this signal to, millions of people who downloaded this SETI at Home. I think it was a screensaver or something like that.
Right, absolutely.
Does that thing still exist? Is that
Yes.
Run out of...
Yeah, SETI at Home is still operating, also based out of Berkeley.
Okay.
So SETI at Home was actually one of the earlier deployments of distributed, decentralized computing. And it employs a set of match filters that people use that people have engineered of signals that could potentially be interesting, potentially be sources of ETI. And that effort is still going on today.
Interesting, but your focus is on the application of machine learning to this. How did what sparked your interest in this area?
Absolutely. So as machine learning applied to SETI, for example, SETI at Home, as we just discussed, employs a set of match filters. And Breakthrough Listen also mainly revolves searching for particular types of signals, which we can go into a little more detail in a bit. The idea is that using machine learning, we can potentially find signals where we don't exactly know the type of signal that we're looking for. So that's one of the main reasons that a more flexible and versatile technique like modern machine learning could potentially help. For me personally, my background was actually originally in particle physics. So the my career track is sort of um, I started very young being interested in big ideas, ideas that based on a set of principles, mathematics, we're able to derive highly non-trivial understandings of the universe and really shape the course of human history. So that really got me interested in the success stories of 20th century physics. During my time at Berkeley, I started to realize that in the 21st century, data has become a new tool to solve these very complex problems more effectively and efficiently. And that's how I got myself involved in machine learning and data science. And I started by I took some classes at Berkeley on seminars of deep learning, where we looked at some recent papers, and we have invited talks from researchers at Microsoft and Amazon, and we design our own research projects, and that started my interest and passion for modern deep learning. And within my department, the one of the groups that was in need the most of these techniques was Spectrograms, the SETI project, and that's how I started my involvement.
Okay. And within the department, just out of curiosity, is deep learning, is it a, still a rare skill, or is it becoming to what degree is it becoming a standard piece of the astrophysics toolkit?
Right, right. To my understanding, I would say I would not call deep learning a standard toolkit in astronomy quite yet. I would say the application in astronomy is just starting to take off. Uh, the good thing is we have very nicely built algorithms from the computer vision community, from the voice recognition language processing community that we can tie into the kind of problems that astronomers are interested in. So I think the progress will be very fast. However, I would describe the degree of maturity to be still in early stages.
Okay. From my previous conversations with folks applying machine learning to astronomy, one of the challenges that, of course, isn't unique to astronomy, but is accentuated in astronomy, I believe, is the issue of the data, the cleanliness of the data. Can you talk a little bit about the data sources that you're working with, and what they look like, how you have to deal with them, and the challenges that they create for you?
Absolutely. So, because I think because the algorithm side is so well developed from the computer vision folks, I think for us, really formalizing the problem and putting the data in the form is I think the main effort in applying machine learning. And so for us, um, uh, in the radio frequency study, the data are collected as complex raw voltages. So these are time series, very high data rate time series that we collect from the telescopes. The raw data rate would be about half petabyte per day. And we take these complex time series and we essentially take Fourier transforms on these time series to form spectrograms. So spectrograms are intensity as a function of frequency and time. They are essentially two-dimensional data, sort of like images, where we do a lot of our analysis. So these two types of data products, the time series and the waterfall plot, the spectrograms, are the two main types of data that we work with.
The spectrogram, is that a native output of the telescope, or is that a product that you have to create through processing?
So it's a product that you create through processing. You can think of it sort of a feature extraction. So it's a Fourier transform to represent time series essentially by the type of periodicities, the type of frequencies that's present in the data. It's a kind of feature extraction, but it's a very efficient one because of the way the Fourier nature of wave physics essentially.
Mm-hmm. And so you've got this half a petabyte of data per day that's coming off of these telescopes that you're using. Do you have to work with all of that, or are you able to? Are the telescopes themselves, like the organizations that run those telescopes, producing products that are, already processed and lower volume, or do you just kind
Right.
of work with raw data?
Right. So the spectrograms I mentioned, that's already 100 times smaller in terms of data volume than the raw
Okay.
data. We do this simply by averaging once the spectrograms are formed. So that makes the data storage problem a little more manageable. And by doing so, you do destroy some information. So the spectrograms that we work with, we designed them from the get-go for a particular type of observation, in that we try to isolate the signals that are coming from the sky, aside from the signal that are coming from the side lobes. There's these signals, terrestrial signals from cell phones, satellites, from airplanes. We try to isolate these interference away from signal that's actually coming from space. So we do this by a spatial filtering technique, where to simply put, we look at multiple patches of sky at the same time, and if a signal shows up in all patches of sky, then we conclude that this signal is actually not localized in the sky. So the spectrograms are designed to look for these particular types of signals, and we have a set of match filters that operates on these spectrograms to look for them. However, the nature of the problem is not so well defined because we don't exactly know for sure that the type of signals that the advanced civilization could be sending matches the match filter that we're deploying. So we do store all of these spectrograms for later inspection with more advanced techniques such as deep learning, even unsupervised learning, to look through them more exhaustively.
Mm-hmm. You mentioned that one of the big challenges, besides from kind of just the data processing piece, is problem formulation. And you alluded to that again, and that this is something that will change as we get more sophisticated. How do you approach that part of the problem, though, in your research?
Right. So the fact that the data comes very unstructured, so these are essentially just images and images and images, where you don't exactly know what to look for in the image. It requires essentially different problems being formulated depending on what the goal is. So one particular project that we recently did a press release on was detection of a signal known as a fast radio burst. So these are a particular type of signals that astronomers have detected since 2007. So these, what they look like is, in the spectrogram that we just mentioned, these are roughly a parabola. So these are quadratic form signals. To look for these type of signals, we know what type of signal we're looking for. So to use machine learning, we can simulate the type of signal. And the reason we want to do this is one that we know what to simulate, and also because the signals are themselves very rare. So to date, there are only about 50 different fast radio bursts ever detected. And from one of these sources, there have been about 200 to 300 detections. So this is not a lot of samples to go off from a deep learning perspective. And therefore, simulation would be needed to greatly expand the positive examples. On the other hand, we do collect, in terms of spectrograms, we collect about petabyte per year of spectrograms, and there are many examples. There are terabytes and terabytes of interference, the signals that we don't want to pick up in this data, and by using the real background, the real interference background, and simulating on top of simulating fixed signals on top of the interference background, we train these networks to reject the signals that are actually interference and uninteresting. So that's one particular example how to look for signals that are rare, but we know what to look for. Sometimes we detect certain signals, and we don't exactly know if this signal is interesting. That requires a slightly different problem formulation. And that way we have to first design a match filter, or we can design a machine learning algorithm to pick out these signals. Then we do anomaly detection. So we do a future prediction type of anomaly detection where based on the past observation, we try to predict the future observation, and then we compare against the real observation to see if there's any significant discrepancies. And if there is, then anomaly is triggered, and we will look at the signal more closely. There are also problems where we have we collected a great deal of signals, and we don't know exactly how to characterize them, whether they can be classified, or some of them maybe we can classify, and that could be treated as more of a semi-supervised clustering type of problem, where we try to characterize these signals and try to put them into different classes.
In the case of the fast radio bursts work, is the idea that you're able to train a detector for these radio bursts? Will you then take that detector that you've trained and run it against the petabytes and petabytes of historical data to identify instances where it occurred before you started paying attention to it? Or is it more just, from now on, we're going to start looking at these things by running this detector against them?
This particular announcement was about a particular observation that we performed about a year ago. So for that observation, we collected about 8 terabytes of spectrogram data that's now all open to public from our website. So in this observation, we previously had a match filtering technique that detected 21 signals. And by training this network, we reanalyzed the same data and detected 72 more. So all of these detections were from the same source. So they have certain characteristics that are all similar to each other, which made the design of the both in terms of the problem formulation, what kind of resolution should I feed in the spectrogram in, how many layers we should have to make the entire design a little simpler. We will also like to do both of those things that you suggested. One is to search blindly in all the archival data for similar signals, and another is to use this in the real-time scenario for future surveys. Both of those will be a little more challenging. For example, one difficulty is the problem of scale. When you don't know essentially the curvature of this parabola, the signal could be even 100 times, last 100 times longer than the signals we detected in this case, or be much narrower, so on and so forth. And that requires sort of a multi-scale kind of input in order to have the same sensitivity across all of the parameter spaces. So that we haven't done yet.
So you formulate your problem into one of these broad categories of, identifying the patterns or doing anomaly detection. and then you have the two different types of data, the time series data and the spectrogram data. Are there other things that you're doing? What else are you doing on the data processing side to before you are putting data into it sounds like you're using traditional, more or less, CNNs and those types of neural networks. Is that right?
Right. So some of these require, so both in terms of the pre-processing, in terms of the feature extraction, and in terms of the deep learning, depending on the problem, there are different uses. So for the fast radio burst work, we used a typical CNN. It was a residual network. For anomaly detection, because there's a temporal component to it, we use a convolutional LSTM, and it's also trained out of a serial way, like a GAN, because the loss function these spectrograms, they are image, they are two-dimensional image data, but they are very, very noisy. So that makes a direct comparison in terms of the pixel-wise L1 or L2 loss. It makes that not very useful, because you cannot predict noise, right? So we use sort of a adversarial loss to train these type of networks. For the clustering type, depending on, we want to be robust, for example, to a variety of things, to how the signal was filtered on the analog side, and to how we process them, and what was the fractional bandwidth. To be robust to a wide range of parameter there, we do some feature space techniques. We use some additional laws to regulate what the feature space looks like. We also try to use some of the adversarial techniques called domain transfers. These are the same techniques that people use to do. So if the training set, say, was rolled images taken during the day, how would you be able to do inference for when how would you be able to inference when your camera is recording at night, right? So to be able to cross this domain, we try some of the techniques that people developed in computer vision as well to do this. Yeah.
Okay. You mentioned GANs. Can you elaborate on what you're doing with GANs?
The particular work I mentioned has an adversarial component to it. It's sort of so GAN. The original GAN is meant to generate new data that conforms to the distribution of the data set. It's not quite exactly what we're doing. This is a future prediction type of network. So what we're trying to do is to, given a past observation, predict what the future observation would look like. So you would still want to compare this prediction with the actual observation. So in a way, this is a self-supervised type of technique. We use an adversarial loss in that the generator that we have that generates this future prediction, we also introduce a discriminator that looks at the real observation and the predicted observation, and try to tell which one is which. And by having the generator trying to fool this discriminator, we essentially generate more realistic looking future predictions.
And is this GAN operating like in the frequency domain? Is it trying to predict spectrogram samples or something else?
Right. So this was a convolutional LSTM that's making the prediction. So that's just the generator it is. The GAN component of this is just an additional term in the loss function. So the discriminator is a CNN that looks at the spectrogram that's predicted.
You talked about domain transfer, domain adaptation. How are you approaching that in this use case?
The main idea of domain transfer is that when your training data has certain characteristics, and your your test set data is from a different distribution, and you want to be able to correctly do inference on this new slightly differently distributed data set. I think this problem we face a lot in the radio frequency domain because the signals could potentially look very different if a different sensor was used, if different bandwidth was used. Essentially, the same signal can look completely different in the time domain, which may be the original the data that was fed into the neural network. So we use these techniques to essentially do the same thing as in computer vision, to be able to do inference more effectively in a domain that the training data was not collected on.
And is this primarily happening at the kind of as feature pre-processing, or adding, subtracting gain from your signal, or applying filters or things like that, or is this stuff that's done in the training process?
So this is done in the training process when we also we for example we use a lot of simulated data because it's hard to collect ground truth labels for real data, and to when we train with this loss function that has knowledge of what the real data, essentially the target class looks like, but we don't know the labels. You can add this additional loss to the training process so that the learned model is more aware of the target domain.
I guess I'm trying to get a sense for how many features these models tend to have. Are they
Ah,
are they very high dimension, or not necessarily?
that's a very good question. So uh, the in some of my experiments in these type of classification and semi-supervised clustering algorithms, we find that this type of domain adaptation we typically use on the last layer. Essentially, we find that around 128 features was probably was the most efficient in terms of using this technique.
Okay.
But that doesn't mean that this is a general statement about all of these applications. It could simply be the type of signals that I was deploying this technique to classify, roughly had that many dimensions. So I think it's still an open question to the degree of variability in the number of features.
In the fast radio burst paper, there was some mention of a new periodicity search technique based on Rally tests. Is that related to machine learning, or is that more kind of domain specific?
I would say that's more of a data mining technique that's not really machine learning. However, it is a technique that's new to the astronomy community. So we detected all these signals, and we would try to see. One of the main questions we want to see is there any regularity? Do you see periodically appearing signals? And because these signals come from very, very far away, so the source, I should say, for this particular signal has been localized in a dwarf galaxy that's 3 billion light years away. So, and the signal, when they come to us, many of them are very, very weak. So we don't exactly know how many of the signals that was emitted was actually detected. And that makes searching for periodicity in the signal relatively difficult. So we use this technique based on the Rayleigh's test to see if we can detect any periodicities, and if not, if we can put a significance level in terms of there not existing a periodicity. And in the end, we went with a later one. It does not look like any of the periodicities that in the range that physically was sensible was a statistically good match for the data that we collected.
To what degree is the periodicity represented in the spectrograph? Like I would have imagined that the frequency component, the stronger frequency components would represent periodicity that is kind of readily apparent from the spectrograph. What does this technique do for you kind of beyond what is available via your Fourier transform types of techniques?
Right. So that's a very valid question. So in the spectrogram domain, if you see a very regular period, then it will show up very clearly. Um, so in our case, these are very rare signals. So in these 6 hours of observation, around 8 petabytes of data, we have about 100 detections. So these are very rare and very weak signals. So similar techniques that have been applied to finding pulsars, which are radio bursts. There are some differences. Well, the pulsars are their source are situated within our galaxy, and most of them you can see clearly a regular period. And some of these techniques in spectrogram that works on spectrograms could work there. But for us, because of the amount of noise that's present, it just was not nearly powerful enough to put a constraint.
Got it. Got it.
Yeah.
And I imagine that there's, I don't have the words for it, but I imagine that there's some notion of kind of a complex periodicity that's not, just a regular time domain frequency, but maybe has other components that might be harder to detect, but still interesting. Is that something that you're able to detect in this data?
Right. So I mean, essentially, if you have many parameters, you can always fit the data, right? So
Yeah, yeah,
so it's we that is one issue, and the way we I should just mention some factor that could potentially cause this type of complex periodicity. One is the emission could not have been periodic, but maybe it was the emission itself was pseudo periodic. There was a window in which through which the signal was emitted, and during the propagation process, there could have been processes that delayed some of these signals more than the others. So by the time they arrive, they appear to essentially you've smeared out any periodicity that was in at the time of emission. So we don't exactly know. There are some models that are based on astrophysics to model these more complex type of periodicities. There hasn't been enough evidence to support any of them, and even though we have the most amount of detections from a single observation, it still would not be able to constrain these models. So what we did is to essentially put all the complexities in the same parameter. And in our case, it's the uncertainty. It's the uncertainty in the arrival times that we picked up. And all of these different models, they would map onto this uncertainty in a way, and we derive our final constraint as a function of this uncertainty. And that way, this measurement could contribute to putting limits on these individual complex periodicity models.
So you see kind of in parallel to the application of machine learning and deep learning to astronomy, the application happening in domains like computer vision that's moving very quickly. Are there technique and you're sounds like you're staying very well current to some of those techniques by applying GANs and domain transfer and things like that. Are there things that you're excited about happening outside of particular things that you're excited about happening outside of astronomy that you think will have big impact on this field?
Yeah, absolutely. So I should say the radio frequency AI applied to radio frequency data is not only something that's done in astronomy. In recent years, there's also a lot of interest in the defense sector as well as in telecommunications, and there are a few companies that I know, mostly in Washington D.C. area, that specialize in this type of signal recognition, and for them, they want to be able to classify all the signals that they detect and see if there are any anomalies. For us in radial SETI, we will also like to do that. They may not be the signals that we're looking for, but we typically would describe this as a needle in a haystack kind of a problem.
Mm-hmm.
And by classifying all of the signals that are terrestrial signal communication signals, we will be able to understand the hay in the problem very well, and this would help us narrow down our search greatly in terms of understanding potentially interesting signals in our data.
And are there techniques that are emerging or evolving in the broader or out of the broader deep learning community that you see having a big impact in this area?
Outside of deep learning?
No, inside of, within deep learning, but outside of the astronomy in particular.
So for example, these applications I mentioned are works that are in they're engineering, more from an engineering signal processing point of view. So they are a bit outside of astronomy themselves. In effect, we try to pay close attention to some of the recent progresses. It's usually, I think, we're late enough to the game that there are still enough cherries to pick from well-established ideas. I think it could be. It's both a good thing and a bad thing. A good thing is that we do have a lot of established techniques that we can apply effectively by designing the problem appropriately. The difficult part is that the data was not collected with machine learning in mind. So first of all, there's not any labels, and things have vastly different scales compared to one another. I think the putting the data in a form that's suitable for these, by this point, well-established ideas is it's still a very fruitful effort, I think.
Well, Gerry, thanks so much for taking the time to chat with us about what you're up to. It's very cool stuff.
Great. Yeah. Thanks a lot for having me.
All right, everyone, that's our show for today. For more information about today's show, visit TWIMLai.com. Be sure to visit TWIMLcon.com for information or to register for TWIMLcon AI platforms. Thanks again to C3 for their sponsorship of today's episode. To check out what they're up to, visit c3.ai. As always, thanks so much for listening, and catch you next time.